No.
That sounds like a ripoff.
It's 14 gigabytes for $2.
For $5 you can get
it for like.
Everyone got
McDonald's
something?
eating a hamburger for $8, which is more calories. I like calories. I don't like sugar. You can get a bag of mini donuts. Oh shoot, I don't have mine stapled.
Do you want a staple?
I will take one.
Just the staple, though, not a stapler.
It's just one.
It's just,
Here.
Oh, Alex,
You gotta back up. I always has one, but one day I forgot it.
Oh.
would you mind grabbing that for me so I don't have to like try and like swim over this middle? We won't slide it this time. If I can't catch currently. Hands of rock.
Hands of rock.
Hmm? Paying him to clean up.
I wrote my name on it. Pretty sure I did. Pretty sure I did.
100% to everyone. Good job, guys.
Sounds about accurate.
So based on the way that you like drew lines on the homework, did you mean 6 to be extra credit?
Didn't I announce it before?
Yeah.
You might have, but my brain sometimes has a faulty memory.
You just know.
You know, I need to upgrade to a little solid state drive in there.
I feel you there.
I think I'm gonna put brain junction there. I have to fill my girlfriend has to fill up her car with gas before we leave, so I'm gonna take her car. Go to get gas on the holiday. Just drive over, grab Grand Junction, and then go like wait. No, I get the junction to light.
Can you get something for her too, or you just gonna
No,
say
she
just
doesn't
to her?
like Grand Junction.
It's not healthy.
No, she just doesn't like it apparently. She said the first time we got it was really good, but the second time she didn't really care for it. So she doesn't ever want to go back.
How many people in class?
2, 4, 6, 7.
Okay, agree. It's my calculation.
Mine was a really scientific calculation. I can provide a bunch of things. Yeah, I used derivative to solve for my number though.
My back.
So let me know if you get your own thing for grading.
No, but I always seem to get the same persons for grading.
I did not get the same person.
Oh, dang.
Because you are in the middle, and I'm starting walking and distributing either from one edge or from another one, and one in the middle to get repeated pattern.
Eat it. Snort it. That might hurt, but okay.
So here are the answer keys, and I will be giving some suggestions.
But she likes the chicken bacon. She got the Cajun chicken, I think. Or maybe chicken bacon. I don't remember which one she got.
Yep.
It looked pretty good. Oh, where's one?
If anyone finishes too early, I have one more for another class member who was not able to come in time.
What is the answer to number 1?
Yeah, number 1 is not on here.
Number 1 is not on here.
That would be sorry.
Maybe.
Which number one is not?
What is the size of a 1D box that will provide the?
Isn't it just on the right hand?
Is it right here?
Problem 4 doesn't seem to be on here either.
Well,
Unless
that
I'm
is just as labeled number 2.
Well,
Oh,
okay, I think this one is number one, right?
On the right side.
Yes, on the right side. And, maybe you know the answer better than I do. So it's great based on your understanding. The problem was to find the what size of the box, if you know the energy. So you write down the energy for the first state of particle in the box, which includes size. Then you solve for size and plug in values and convert units. This problem is for 10 points, and if the equation is there, you can give 7, and additional 3 if there are some reasonable number. Yeah, well, I'm not good in arithmetic, and I'm not going to punish you for not being precise in numbers. Find any opportunity to ramp up the grade. So for problem 2, there are several ideas that you may want to give credits for. So the total credits for the problem is 30. And in case you see the right answer for the so what was requested? Position and momentum matrix elements, right? And 1, 2, and 1, 2. If you have reasonable answers, find way to give the maximal grade. If there are right answers only for x, give 20. If there are right answers only for momentum, give 10. And let's place less points for diagonal elements. 5, and then the rest 15 for the off diagonal here and 5 there. So for off diagonal the credit can be given not only for the answer but just the way of thinking. So out of this 15, we can split if you have the conversion of one integral on 2, you can give extra 5 points. And if the candidate whom you're grading identifies to take into account integration by part, also give 5 points, even if it is not fully implemented in all details, just for good attempt. Okay. So the answer for all diagonal things is 20 over 9 L over pi squared. And if one approximately takes pi squared as 10, it will be like 1 over 5, right? Roughly. And there are two important points which you can also give credit for. Off-diagonal elements are not zero, and off-diagonal elements are proportional to the size of the box. The larger the box, the larger off-diagonal element. They're proportional to L.
This is out of 40 points. I said,
Well,
30.
30 up to 30, yeah.
yeah, it's not. Next year I should give 40 for this because it's really challenging. But, I will be looking what how you do grade and approve and make notes so that you do not suffer even things are partial. So this one is not a true grading. I just took one of your colleagues who submitted earlier and identified some common errors. So this for momentum expectation values. The answer here was not right, but some ideas were reasonable. So first, I'm not as tall, but I do not want to jump too much. Okay, so in matrix element, there should be a momentum operator and the candidate placed factors, but has forgotten the derivative. So you can subtract points if it is not there. And then actually everything will be wrong after this point, but you can still see some positive aspects. So if the derivative would be there, it will be cosine instead of sine here, and it will be factor 2 pi over L. If you jump immediately to the answer for matrix elements of the momentum for diagonal parts should be 0, and for off-diagonal elements should be non-zero. More answer is not here. I just corrected the most important error. Here the answer has dimension of Planck constant, but it is not right. The dimension should be Planck constant divided by length, because dimension of Planck constant is momentum times position, and if you divide by position by coordinate, the dimension will be momentum. Right? It will be something divided by L. Planck constant divided by L by some factors. So if you see answer like this, already be generous. What else? Well, if one has practiced derivative, then instead of sine times sine, it is sine times cosine, and by the trigonometric equation, it will be product of sine and sine instead of cosine and cosine. So one would need to integrate different trigonometric functions. The substitution of new variable is okay, reasonable, and we think that was missed here, that because of lack of derivative, the factor 2 pi over L was missed. If one goes over and puts this 2 pi over L everywhere, other factors cancel, but this 1 over L resides. And we see that the answer is proportional to Planck constant over L. The answer will be something like 2 minus 1/3, which will be 5 over 6 times Planck constant over L multiplied by imaginary unit, something like this. What did you get?
I was just saying 2 minus 1/3, would that be 5/3?
Yes, 5/3. Good.
Oh, remember.
So I'm done with
so.
number 2. Should I give more time or you good idea? So 3. It's same as we did in class. So you plug in the initial expansion coefficients, 1 square root of O square root of 2 and I 1 over square root of 2. By the way, there was a question, how come whether the normalization will be okay? If you decide to do double check about normalization, you need to play the C1 star C1 plus C2 star C2. If you just take absolute value square, it's not right. Sometimes it works, but generally one needs to normalization use this conjugation. And then if you have imaginary element here, conjugation cancels and obviously normalized. Then you plug in that expansion coefficients evolve in time according to energy of state 1 and state 2. And then you just express the expectation value of position as product. These two things times matrix element, which you found from previous step. L over 2 for first and last, and the 20 over 9 L divided by pi square for this one, but approximately it's L divided by 5. So L over 2, L over 2, L by 5, L by 5. And then this one will be 1/2, this one will be also 1/2, 50%. And this one, if you add, if you make product of these two things, once this conjugation and then this opposite conjugation, and these two things can come out of bracket, you should give, you should obtain a two-dimensional function. Okay. So if you see the figure of L oscillating around midpoint around the L over 2, and you have equation something like L over 2 minus factor and the two-dimensional function, which is likely to be different because of this imaginary element just with full frame. And if the last thing is not there, but you see some reasonable steps, logical steps towards achieving result, also be partial correct. Times 3. Well, for position it's similar. Just to proportionate the answer. It will be similar figure oscillating not around L over 2, but around 0, and it will go as much as we've got expectation value of momentum. So it will be imaginary, not real, and it will oscillate around 0. A little common, what is the take-home message out of homework? That even in the box, if you create superposition for state, the position will change, but momentum will change as well. Some of you were sending questions like, is it possible that momentum over time will not change? No, it is not possible. If position is changing, then momentum is derivative of position. It should change as well. And actually, there is a trick of doing the second part. You just find expectation value of position and then take the derivative and compute the answer from there. Good. Well, divide by mass. See some of you like this as a short. So for number 4, expectation. Practicing Heisenberg equation quotient for expectation value of position and momentum. Instead, in previous 2 and 3, we were practicing expansion over eigenstates. Now we are practicing Heisenberg equation quotient. So if it is a free space, momentum doesn't doesn't change over time. It is what it was originally. And the units are chosen in such way that position will be integral of momentum over mass, will be just equal to t. In free space, it just goes linearly. And if velocity equals 1 in the selected units, it will be just proportional to time. 10 for completion. So number 5 is a little more challenging because it has non-zero potential. So the idea behind number 5 is that position and momentum, even if they are quantum with the expectation value, they evolve in time in the combined way. They are depending on each other. So if you write down equation of motion for position, dt x, right? You have it in class, and if you successfully completed number 4, you already have it. It depends on the value of momentum. And if momentum is not constant, if it depends on time, we need to solve for momentum as well. Therefore, one needs to write down Heisenberg's equation of motion for momentum operator. What was the number of points for number 5? 20. Should be more. Well, maybe the whole work should be given some factor because it is a little harder than usual. So this is standard thing. Is what you already know. The expectation value for position. And if we need to do something for, if this equation is reproduced or derived, give some partial credit. And then one needs to have an equation for expectation value of momentum. So for this step, even if it is incomplete, give 10 out of all 20 for this problem. So for the effort to get equation of motion for expectation value of momentum, we plug in into the Heisenberg equation of motion eventually, which is kinetic plus potential. We already know that kinetic energy and momentum compute, therefore this terms goes away, and you have only commutation between momentum and potential, which means you need to commute this potential times derivative minus derivative times potential. In order to do so, one may want to put here an arbitrary function and assume that in the second term the derivative acts on both potential and known function. Yes. Then one opens the derivative of the product as derivative of potential times an unchanged function minus potential times derivative of the function. And then first and last term cancel, and we can remove our auxiliary complement. So the derivative of the expectation value of momentum will be, and then all of constants will be minus expectation value of derivative of potential over space. question that you remember from previous lecture. What is derivative of potential over position?
Force.
Yes, it is force. So force as a reason to change momentum. And then if your potential was mgx, then derivative of space will be mg. So it's similar to free acceleration. Okay. And change of the momentum will be, if you integrate it, will be linear in time. So, as it is always happening with Heisenberg equation of motion, we have the system of coupled equations for position here and for momentum. So the solution of one moves into another one. And if you integrate them, you get that position changes in time quadratic. Right? Mg t square over 2. So if you see this t square, give full credit, no matter what was before. If you don't, then play partial credit game. Okay, this one. The last one, extra credit. So let's save time. I'll just glance through very quickly. So you already know the how to. Oh, should be quickly. Let me just go to the answer because everything is right here, but it will be a long story. So just do the answer. And the solution here is for some constant, but in your case it will be just silent cosine. So position and momentum will be oscillating, and there will be no omega, just t. And if you plot them simultaneously, it will be oscillations which are phase shifted according to each other, or one can make x, p, and time axis and make a spiral. So if you have this answer or plot a spiral, give full credit. No, just partial.
How many points is that on?
Huh?
How many points is this out of?
40?
40.
So a little more favor from your side to me. Please add together all points and summarize them on the first page. Ready? You can keep the answer to yourself.
Okay.
I knew the class will perform perfect. So you guys are on a good track to good grades.
Yeah. 35 out. Enough.
Whew. So how much time do you have? The new material? Oh, generous 15 minutes.
Awesome. That's a lot of time.
So who we are and what are we doing?
Fortunate students looking back at a staircase.
Good. Perfect.
What we did last time. Staircase.
Well, you will see your favorite staircase. Oh, not you, the tortured student.
Oh,
What were we doing? Oh, your favorite question. What were we doing last time?
Harmonic oscillators.
Which are harmonic oscillator? What is oscillating? Typically.
Bond between two atoms.
Yep. So atoms, nucleus, ions. One can design harmonic potential for electron, but it is very uncommon. Typically, it's something heavier. How much proton is heavier than electron? Huh? How much proton is heavier than electron? Huh?
A lot.
But what like once we told that infinity equals 30 in one of the labs, but a lot equals to roughly.
1,000 times.
Yeah, very good estimate. 2,000, or if one wants to be very particular, 36 or 37. So it's a lot. It is heavy. So quantum effects are less important for proton, but still there are their signatures. And we are going to about this later, and we need to start with time-independent general equation, which is a big challenge. It is much more challenging than it was for harmonic oscillator. So it will be not impossible to spend like 2 weeks on solving this. If you do it quicker and speed, meetings, it will be a great achievement. Oscillations, complicated potential that we approximate as harmonic shape. Taylor expansion, dropping first derivative because the zero, changing system of coordinates, and then having the quadratic term with this is elasticity constant, right? So derivative of potential is elasticity constant, and we are changing it to the units of mass and frequency, because mass you can pick from periodic table and frequency can be measured from infrared spectroscopy. Here the potential, and then we plug it into the time-independent general equation, where we do have the second derivative for position kinetic energy and this r squared as potential. So in those differential equations that we were solving up to now, we never had a term proportional to independent variable. So if you drop this term, if you have only unknown function and derivatives, first, second, 10th derivative of unknown function, the standard way is to plug in the solution in form of exponential and then just do routine procedures. It will be just specific power of exponential and maybe a combination of those. But for this stuff, it will be different. We will have no time to do actual work to do that. There is time to give introductory steps and ideas. So it would be reasonable to start with finding ground state, so ground eigenstate, the function, and then later on we will pick up for eigenenergies. So here is the answer, and I'm skipping normalization constant. And this is declaration of the substantial intellectual effort. So we will not be idle, work hard together to entertain the show. Maybe not today, maybe on Monday. Today we'll just sketch the plan. But the eigenstate of harmonic oscillator has shape of your favorite Gaussian function. which means that it is not literally at equilibrium measurement. It has some probability to be a little bit closer, not in the shorter or longer. So there is some distribution. And the bit of this distribution is inversely proportional to mass and frequency, which means if instead of atoms, we look for uncertainty of a microscopic object, the mass will be in denominator, and which will mean that the uncertainty, the bit is uncertain, right, will shrink to zero, very, very close to zero. So the criterion to have this unknown width, meaning that mass is maybe a couple of thousand times bigger than a proton, but still something small. What should be this frequency? Should have non-zero width. Should it be large or small? In order to increase the signal, what should we do with one? Okay. Small estimation. Okay. So small mass and not very big estimation. So, there is a standard, correct, but very boring procedure to solve this equation. If you are taking differential equations, is anyone who taken differential equations in the class? Okay. Who took in the past? Okay, good. What are you solving equations like this? With what a term in the equation that is neither derivative nor function, no unknown function, but proportional to the independent variable. Do you remember such equations? Did you practice? Well, maybe, but it is big. It is a true torture. It's huh?
So probably not.
So the solution is to there are no functions except the ground state functions with non-Gaussian, but all other functions are not standard. So one needs to design special functions to solve this equation. And if functions are known, if they are neither polynomial nor sines, cosines, and exponentials, then one define them as their mathematical properties and then expand them as summation over series. So the typical solution of such equations is solved as unknown function is represented as a series with unknown coefficients. And then coefficients to themselves are found to obey some recursion relations, which is a set of linear algebraic equations which can be solved. But I would like to offer a shortcut. It will also include some mathematical difficulties and a little pain, but please believe me, what I offer is like 4 or maybe 10 times quicker than C. So really short. If you will be exposed to quantum theory again, likely you will not see the shortcut. You will be exposed to heavy stuff. Then you will appreciate it. So the shortcut that I'm going to offer, you will practice it for at least 2 weeks, maybe 2 weeks. Has more thinking, more philosophy, more discussion rather than pure math. Has some ideals, some thoughts. So the name of the shortcut is ladder operators. staircase. So it's favorite subject of ours. Suppose, hopefully, everything is empty. Suppose that we have found the eigenstates, we have found the functions. We already know that if you do Gaussian, it will be something here, there, I don't know what. I know, but I'm telling. Then suppose that we are doing an experiment of exciting and de-exciting this system. For example, in the infrared spectroscopy, you find, the oscillator has its frequency, and you can, like when the swings, you can give it more and more amplitude. And if it is infrared spectroscopy, you just put it in resonance laser, you start to accelerate. But what happens to quantum states? Definitely, you are going up from ground quantum state to higher up, as you excite it higher and higher. So the tool that I'm going to offer, and that you will see is abstract concept of. So it's abstract thing. It is not anything real. Of operators that will symbolically promote your harmonic oscillator between its states. So it will be raising and also there will be lowering. So if we were in one of the excited states, we can apply lowering operator and go by one state lower. If you were in some state like first, so we apply raising operator, we go by one state higher. Okay, makes sense. So we do not have, and we can give them names like A, dagger, and A, which is standard. But we do not know how they function, or whether they will implement differential operators or something else. But just assume that they do exist. Okay? Hypothetical. Now, first philosophical trick. If you do have such operators, especially lowering operator, if we apply lowering operator from second state, we are going to the first state. First excited. If we apply lowering operator to the first excited state, we are going to ground state. What if we apply lowering operator to the ground state? What are we going to get?
Zero.
You took quantum theory, zero. It's explain your ideas why you decided that it is zero. Because I always have a difficulty to explain it.
Well, if you lower it from the ground state, wouldn't that be the same as removing the electron?
Okay. Lowering the ground is same as removing. Well, there is no electron. It's just point oscillations, but intuitive guess answer was correct. We can argue why, but if it's same like if I do have a staircase that leads me to the basement, the next steps go down to the basement, and then I go to the ground. If I want to, can I go deeper? So the result of my attempt to go deeper than ground will be zero. It's not possible. It's just trying to fall down and smash myself on the floor, but it's zero. It's not possible. We cannot go. So if we make some tricks and design a functional shape of this lowering operator, if you do have unknown wave function for the ground state, and if you apply this lowering operator to unknown operator for the ground state, we will get zero. So I declare and invite you to believe that designing shape of operator, which will include some derivatives, and applying it to a known function and solving this equation will be so much quicker than solving actual Schrödinger equation, family dependent Schrödinger equation. So mathematically, it will be just a deserved. Well, any math is not deserved, but compared to what we may have practiced. So if we do this trick in the right way, the answer will give the Gaussian distribution. How will we do this time? No time. And I have like 30 slides, which probably will be postponed to the to Monday. Let me just find the favorite. Yes. Have a nice weekend. No homework because you worked so hard and deserve a little relaxation. And it is a halfway in semester between chapters. So just accumulate strength and energy, and maybe you have your favorite activities like doing homework in other classes.
Yeah, just on Tuesday, I got a paper on Wednesday. Oh, I have another paper due on Tuesday.
I have to do work a blank worksheet for conference.
For what? On 110?
Yeah.
Have a good weekend, Dimitri.
Thank you, Alex. Have a good weekend to everyone.